Welcome to the most fun video, in my opinion, in the special relativity in the APS series that I'm doing. In this one, we will derive the electromagnetism, uh, or the equations for Maxwell's equation in the APS, and we'll discuss what that means conceptually. But before I get into that, I would like to talk about reciprocal and standard bases, because that's something that is important for the definition of gradients. And I don't think it's a subject that's covered often enough. Um, and because of that, I would like to put some emphasis on it so that at least there's some source online where you can learn about it in the context of electromagnetism. So, first, we're going to take a detour into classical physics within the APS. And because we're going back into classical physics, we're using vectors again, not paravectors. Because in the last video, we were using paravectors, or the last few videos we've been using paravectors, but we're now using vectors again. So the gradient, the traditional vector gradient in classical physics is defined as so. But what are these superscript sigmas? Because we're used to seeing them with them as subscripts. Well, that is the reciprocal basis for the standard basis. So this is what we've been working with, the standard basis, and we have the reciprocal basis here. And it's always defined as the dot product of the reciprocal basis with the standard basis is the Kronecker delta, which will give you a 1 if j is equal to k and a 0 otherwise. Well, in classical physics, so non-relativistic physics, we know that the dot product of just the standard basis with itself gives the Kronecker delta. So that means that in non-relativistic physics, this reciprocal basis is the exact same as the standard basis. However, in relativity, it's not true. And so let's get into that. There's this basis right here, which is used for the paravectors, where you have sigma naught, which is just sigma t, which is just 1, sigma 1, sigma x, sigma 2, which is sigma y, sigma 3, which is sigma z. And this forms the basis for the paravector. And using this definition, where the dot product here is the paravector dot product, we get that the paravector dot product between the reciprocal basis with the standard basis is still the Kronecker delta. It's the same definition as here, but now we have the Greek indices where typically you have, j goes through 1, 2, and 3, and then mu goes through 0, 1, 2, and 3. So we know that this isn't the same thing as the standard dot product, because if we take the paravector dot product between the standard basis and the standard basis, we get the Minkowski metric, which is different from the Kronecker delta, because we actually get a plus sign if they're both equal to 0, if both indices are 0. We get a negative sign otherwise, and we get a 0 if they are not the same. So this is where you get the term the Minkowski metric, where here we're using the plus minus 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 signature. And it's called that because when you have the zeroth index, you have a positive sign. That's this 0 when both indices are equal to 0. But then you get minus signs right here whenever they're not equal to 0, so 1, 2, and 3. So this is called the Minkowski metric, and that's what allows for special relativity to exist, actually. And so this is the definition for relativity, and then the reciprocal basis gives the Kronecker delta. But what exactly is this right here? What is this reciprocal basis? Well, we can actually write it in terms of the reciprocal, or in terms of the standard basis, because they differ by a positive sign right here. We can see that actually sigma naught and superscript and sigma naught subscript are the same thing. And because they differ by you get the minus sign here, then you're going to have to have a minus sign up here to cancel out the minus sign that's in this metric. So you end up with sigma 1, sigma 2, sigma 3 superscripts all being equal to negative of their subscript variance. So the standard basis and then the reciprocal basis represented in the standard basis. So you have positive, minus, minus, minus. And the space-time gradient is defined the exact same way that the classical physics gradient is. So notice you have the sigma, and then you have the index, and then you have the partial. And that was what was up here. You have the sum of sigma, index, and then partial. And then for here on out, I'm just writing, like simplifying it down to that. So you can expand this out, and then you can put everything into the standard basis. And I'm going back to writing everything with t, x, y, and z, just because I think it's easier to understand that way when you write it out like this. And then this actually is the exact same thing as the standard gradient that you have in classical physics. So you can just substitute it in, but now you have a minus sign. And so you end up with the space-time gradient being defined as this. And the reason I wanted to go over that was to explain why it's defined as having a negative sign here, whereas for paravectors, the negative sign only shows up in its Clifford conjugate, whereas the positive sign only shows up here in its complex, or in its Clifford conjugate. And the reason comes because of the definition of the gradient being defined using a reciprocal basis. And if you're wondering why there is a 1 over c delta t thing, that comes from the fact that the 4 position, so if you have 4 position, I'll write this as r, then you have ct plus x plus y plus z, and these would all be your vector components. This would be what's in the x direction, y direction, z direction, then you have what's in the time direction, so you have this factor of c that makes everything have the same units. So this is units of distance, this is units of time, multiplying it by distance over time, you get just distance. And because in the differential, or the partial, you have time on the bottom, you have to divide by c, and that's where you get this 1 over c right here. Okay, so now that that has been covered, let's get into actually simplifying Maxwell's equations. Before we do that, it is useful to recall some identities. This is a result from physics, where we just have that mu naught epsilon naught is equal to 1 over c squared, which implies this relationship, and we will actually use this a few times. And then we have the gradient, the traditional classical gradient, times a vector is equal to the divergence plus the what's called the wedge curl. And the wedge curl is related to the traditional vector curl with this I. Well, what is this I? This I is just the product of sigma x, sigma y, sigma z, but you can write it as this. And it behaves exactly the same way as the complex unit I. So you can write it as I. And I'll kind of show why that is. So if you have x, and then I'm just going to write it like this, x, y, z, and then you multiply it by itself, x, y, z. So this would be I squared. If you write it like that, then it just becomes, so you can rearrange by flipping signs. So it becomes negative sigma x, y, z, sigma z, y, x. And then when you multiply these through, you see the z's will cancel. So you get minus sigma xy, sigma yx. But then this continues until you have x, and then you end up with 1. And so you end up with this I squared equals to negative 1. The next thing is to recall Maxwell's equations. You have Gauss's law, which says that the divergence of the electric field is equal to 1 over epsilon naught of rho, where rho is the charge density. So it's basically saying that the electric field spawns from electric charge. And then this is the no magnetic monopoles law, which basically says that there is no such thing as a magnetic charge like the electric charge, so there are no magnetic monopoles. And then there's the curl of the electric field, which basically says that the change in magnetic field generates an electric field. And then there's the Ampère-Maxwell law. So this was Faraday's law. You have the Ampère-Maxwell law, which says that a changing electric field and a current generates a magnetic field. So we are going to rearrange these, and then the more simple form of Maxwell's equations in geometric algebra is going to fall out. Now, many videos on YouTube have demonstrated a simplification of Maxwell's equations using geometric algebra. Most of them do so using the spacetime algebra, but this video will do so with the algebra physical space. So, the first step is to take the curl of E and then use this identity right here. So it's minus I wedge curl of E. And this, of course, is still equal to negative dt b. But this implies that if we multiply by I on both sides, the negative sign and the I will go away here. And so we end up with wedge curl of E equal to negative partial time, or negative I partial in time of B, which we can further rearrange into the form that we need, which is the wedge curl of E plus I partial time of B. The idea when we're rearranging things is that we want all the units to match up, and we want the magnetic and electric fields to be on the left-hand side. So then, coming over to Ampère-Maxwell law, we can do the same thing. We have wedge curl of B is equal to, I don't like that B, that looks better, is equal to mu naught J, and then plus 1 over c squared partial in time of E. Now, notice that there's an I next to this B here. So we're going to try to keep the I next to this B as well. So we're just going to get rid of the minus sign. So we're going to multiply through. So we get the wedge curl, I times the wedge curl of B is equal to negative mu naught J plus 1 over c squared dt E. Or this would be a minus sign. But then notice that there's a 1 over c squared next to the dt. Well, we've seen 1 over c next to dt before. So let's multiply this entire equation by c. And then after we multiply by c, let's move this portion of the equation onto the left-hand side. So finally, we end up with IC wedge curl of B plus 1 over c partial of time of E is equal to minus c mu naught J. Now this c mu naught right here is equal to 1 over c epsilon naught. So I'm going to rewrite this as 1 over c epsilon naught. Now, time for this last change that we need to do, or rather a rearrangement. It turns out that this one we don't need to rearrange at all, so we'll just leave it as is. So this right here, if you have something equal to 0, then like if b equals 0, then AB is also equal to 0. So anything times that will be equal to 0. Well, we have IC times this component that has B. There's an I here as well, and we can reason that a C will show up here, because if we put a C here, then we have a 1 over C, which would mean a 1 over C next to the dt, just like we have here. So we can reason that that IC is actually a fundamental part of this equation. So we can write this as IC divergence of B equal to 0. So we have all of these, but what's the next step? The next step is to add up the left-hand side and the right-hand side of all of these equations. So add, and then I'll put respectively, the left-hand side and the right-hand side. So the left-hand side, I'll just steal these from up here. And then I will also steal these. And then this. And then I'm going to just write the divergence of E. Then add all these plus signs. Then just to make everything cleaner, I'm going to put it back into this color. So you end up with this left-hand side of the equation. And it's equal to, from this, you have 1 over epsilon naught rho, 1 over epsilon naught rho. Then you have minus 1 over epsilon naught 1 over c j minus 1 over c epsilon naught j. Well, let's just go ahead and pull out a c epsilon naught here. So that's going to end up with 1 over c epsilon naught of c rho minus j. And then we can just get rid of this and put this up here. So that is what we have. Now we can start to simplify the left-hand side of the equation. So we can see that from this right here, we have the divergence and the wedge curl of the same vector field, which is E. Well, by the definition up here, by this identity in geometric algebra, we know it's just the gradient times that vector. So we can rewrite this as the gradient of E, and then we can do a similar thing here. So we end up with, or because we have the what's it called, the divergence of B and the wedge curl of B here. So you can end up with IC B, gradient of B. And then you end up with 1 over C partial T E from here plus 1 or plus I partial t b. But then let's expand this. Let's put a c here and a 1 over c here, because it's the same thing as having 1. But now we can see that there's a c 1 over c dt and a 1 over c dt. And there's an ICB, ICB. Oh. Then all of that equal to this. We can simplify again. By pulling out the gradient of both of these, or yeah, by pulling out the gradient of both of these, so you can end up with the gradient of E plus ICB plus 1 over C partial t of E plus ICB is equal to the right-hand side. Now we'll make one more simplification here, because the 1 over C epsilon naught is equal to C mu naught. So we can just erase that and do C mu naught. And then we can make one last factorization. We can say that we have this 1 over C partial t plus this gradient times the electric field plus ICB is equal to this right-hand side. And if you notice, you have a paravector on the right, then you have a biparavector in the middle, and then you have the space-time gradient here. So it looks like we've been able to successfully combine them all. So let's look and maybe more rigorously define what these would be. This, if we go up here, that's the form seen in the spacetime gradient, but the Clifford conjugate. So this would be the same as a Clifford conjugate. And then this E plus ICB, well, in relativity, up here with the traditional matrix approach, or the tensor approach, when we united E and B in one entity, we called it just the field tensor with an F. So let's just call this the field biparavector, the electromagnetic field biparavector. So this can be just F. And then it'll be equal to C mu naught. And this right here, a thing that's traditionally known in physics, is that C rho plus, or C rho, and then Jx, Jy, Jz. This is for current. So it's the relativistic version of the density current. So we can just write this as the for current, just a J without a vector. But because there's this minus sign right here, and our earlier identification with the minus sign with the Clifford conjugate, we have to write this as J Clifford conjugate. And so simplifying this out, you actually get this. I wrote it down earlier. And now we'll just put it here. you end up with this. This is Maxwell's equation. Where you have the spacetime gradient, the electromagnetic field as one entity, and you have the forecurrent. But how is this any different from just a simplification? Does it actually mean anything conceptually or physically? The answer to that is yes. It actually does have implications. So I was drawing some things earlier, and I'll bring these up. In traditional electromagnetism, you have that there's an electric field and there's a magnetic field, and they are perpendicular, and that they travel in this propagation direction, k. Well, this right here, this E remains a vector, but this B is times the unit trivector, I. You have I, C, B, where this B is a vector. There's an identity in geometric algebra where if you have I times some normal vector n, then you get a bivector. You get a bivector. So it turns out that this entity as a whole is a bivector. It's an oriented plane segment, a two-dimensional analog to a vector. So this vector here actually is representing a plane right here, which I've written here. You have a plane which then encodes rotational information, and the electromagnetic field would then look like a vector oscillating, but then you'd have the magnetic field oscillating. And forgive me, this right here should be like, oof, I gotta fix this. They switch signs every the other thing, and the switching signs in this is equivalent to switching the rotation direction. So you end up with that. So you have a plane where the magnitude of this bivector grows. So you have a vector growing, vector shrinking, grows in the other direction. You have a plane growing, shrinking, flips direction, and then growing, shrinking, flips direction, growing, shrinking, flips direction. And that is actually what the magnetic field is. It's not a vector field, it's a bivector field. And what's a little more evidence for this being fundamental? Well, if you have some charged particle moving with a velocity v. So I'll say that this is a charged particle. Say it's a positron, so it has a positive charge. If it's moving with a velocity v in some magnetic field b, then the force it's going to feel, the acceleration it's going to feel, is in this direction. And so what this does is it creates a cyclic motion in a magnetic field. So if you have it starting like this, then it's going to trace out a path that looks like this, like cyclic. It's going to be rotating. And this is called gyromotion. Gyromotion of the positron in this magnetic field. Well, this, if you notice, this rotation direction right here, where you have B is pointing in the same direction here, you have a plane. This rotation direction, this clock or anti-clockwise direction, is the same as the direction of the plane. And so you can see that while it's not intuitive that a vector field creates a rotation, it is intuitive that the bivector field that the magnetic field really represents does represent a rotation. So that's what the difference is physically. That's what it tells us intuitively, is that there's a vector component and there's a bivector component. And so this is the traditional approach, and this is what geometric algebra shows us actually exists. In the next video, I will go over some problems where I will solve some electrodynamics problems, but I will use this instead and show that it does all the same things that traditional vector mechanics approaches can do, and show some also easier ways to do relativistic mechanics using this.